All right, in lesson 9.4, compositions of isometries. All right, so the term isometry means the same distance. And isometry in geometry is a transformation that preserves distance or length, so it's kind of like a rigid motion. So translations, reflections, and rotations are isometries because none of them will change the size or shape of our geometric figure. So you can express all isometries as a composition of reflections. So we're going to look at reflecting across two parallel lines today. We're going to look at reflecting across two intersecting lines. And then we're going to look at something called a glide reflection. Now, the composition of two or more isometries is an isometry. So there are only four kinds of isometries: a translation, a rotation, a reflection, and a glide reflection. So we'll learn about the glide reflection here in just a little bit. So let's take a look here at our first theorem. Theorem 9.2, reflections across parallel lines. So this is the first one we'll look at. A composition of reflections across two parallel lines is a translation. So if you look here, we've got this triangle ABC, and we're going to reflect it over line L. And so it reflects across line L. And now we're going to take this triangle A prime, B prime, C prime and reflect it across line M. And it looks in the same position as it did when it started. And so that is like nothing more than just a translation. It's slid into a new position. So you write this composition as the reflection across line M of the reflection across line L of triangle ABC is triangle A double prime, B double prime, C double prime. That's our final result. Or you can write it like this, and it's basically said the same way: the reflection of line M of the reflection of line L of triangle ABC is equal to A double prime, B double prime, and C double prime. So this function notation, this kind of goes back to when you learned writing functions in Algebra 1. So for instance, if we took two functions, we had a function g of x, which is equal to x plus 3, and we have a function f of x, which is equal to x squared plus 1. Now, let's say they ask us to find the g of f of x. These are the g of f of x, which means I'm going to find the function of f first, and then I'm going to find the function of g. Now this can also be written as g, parentheses, f of x. And so what you're doing is you're going to perform the f of x function, and then you're going to take that number and do the g function with that result. So let's say we put a 3 in for x. So we're going to find g of f of 3. So anywhere there's an x, we're going to start with our f function. Since f is on the right, we do the second one first, and then we do the g last. So this becomes, we're going to do 3 squared plus 1. That's going to give us 9 plus 1, which is equal to 10. So now we're going to take this function and do the g function with it. So g of 10 is going to be 10 plus 3, which is going to be 13. So g of f of 3 is equal to 13. So we always start with the one that comes second. We do that operation first, and then we evaluate the g function after that. So let's go back to this here. So that's what this means. Now, the distance from A to A double prime is the same as distance from B to B double prime and C to C double prime. And remember, all of these are going to be perpendicular to our lines of reflection. So let's look at example 1. Composing reflections across parallel lines. What is the reflection of line M of the reflection of line L of J? And it says, what is the distance of resulting translation? So the first thing we're going to do to make this a little bit easier, we're going to take and we're going to draw a line starting from point J here, and we're going to draw it across so it's perpendicular, somewhat perpendicular to this. Now this line here just helps us keep everything straight. Now what I'm going to do is I'm going to label these points here as we start to do this, and it doesn't have to be perfect. So as we reflect this line across line L, Okay. Well, the first thing we're going to get here is going to be a J that looks something like this, and it should touch that line. Okay, so we have the J that looks like this. It's going away from the line, so that the tip of this is going away. And then as we reflect it across this line, it's going to be, this point is going to be the closest point, so we're going to come here, and it's going to look something like this, which should be similar to this shape here. Now, nothing perfect here. So to kind of help us better understand the distance part, we're going to label these as, let's just be point P. We'll call this point A. Okay, this is going to be P prime. This is going to be, we'll call this point B, where this intersection point is, and this will be P double prime. So the first thing we did, kind of looking at our distance, we're going to do the reflection across line L of J, and this becomes the distance of, so the distance from P to A, that's distance here, is equal to A prime P. Excuse me, that should be, reverse that there, that would be A P prime. So basically what this means is the distance from P to P prime is equal to 2 of AP or AP prime, whichever one you want to write. So the distance from P to P prime is that it takes 2 of these distances here. Okay, so the second step, we're going to do the reflection across line M of J prime. So as reflected over here, we're going to get the P prime to B is equal to the same thing as B to P double prime. Those distances are the same. So what this means, it means the distance from P to P double prime, P prime to double prime, is going to be equal to 2 times the distance from P prime to B, or B to P prime. So these distances are the same here. Basically it's saying that this distance is the same as this distance is the same as this. So the last part here, how far did P move? What is the distance from P to P prime? Well, P moved the total distance of the first distance. It moved from 2A to P prime, plus it moved the distance of 2P prime to B, or we can say it moved the distance from 2 times the distance from A to B. Okay, so what this means is the distance from A to B, that is the distance of A to P prime, plus the distance of P to P prime. So since it moved those twice, 2 of those and 2 of those, it's going to be equal to this right here. So the distance from P to P prime, from P to P double prime, okay, there's a total distance of 2AB. All right, so we're not going to focus too much on that, but I do want to make sure we cover it. So let's go take a look at the second one. Okay, I want you guys to try to draw this one. And this will be composition of 2 reflection across parallel lines. So you're going to draw, once again, it's J. Okay, so draw J between L and M. What is the image of reflection across line M of the reflection across line of point J? So what is the distance of the resulting translation? So once again, draw your line across to set up your perpendicular line to help draw the J in the right position. So pause the video now, work this one out. All right, so as we drew our line here, we reflected over this line L, this is line L, this is line M. And so the interior part, this part is closer to the line here, as it looks like this, is reflected over here to P prime. Now we're going to reflect it over line M, which means the distance from P to B is going to be the same thing as B to P double prime. So it looks like this, and once again it's like a translation of the original figure. And so the reflection across line L of J is the distance of PA to P prime A. So P to P prime is equal to the distance from A to P prime, or just A to P, either way you want to write it. Now, the distance from P prime to B is going to be the same distance as it is from P double prime to B. So the distance from P prime to P double prime is equal to twice the distance of P to B. So P prime to B. So the total distance is moved. It's moved a total of this distance twice, 2A P prime plus 2 P B prime, or that should be P prime B, or the total distance is twice the distance of the length of AB, which is the distance between the two parallel lines. Okay, so let's move on to the next one. Reflections across intersecting lines. The composition of reflections across two intersecting lines is a rotation. So as you reflect this line, original figure here of ABC, you reflect it across this line, and then you reflect it across this line, it becomes a rotation, which means this figure's been rotated so many degrees across point Q, or the point of intersection. So you can write the composition as the reflection across line M of the reflection across line L of triangle ABC to become A double prime, B double prime, C double prime, or reflection across line M of reflection across line L of triangle ABC. The figure is rotated to the point where the two lines intersect. In this case, it's point Q. So, composition of reflections across intersecting lines. Line L and line M intersect at point C and form a 70-degree angle. What is the reflection across line M of the reflection across line L of J? What is the center of rotation and the angle of rotation for the resulting rotation? So, as we reflect this, okay, the first thing we're going to do here is we're going to kind of have to figure out, as we reflect it across here, here's our line. So what we can do is we can draw our perpendicular line. It's kind of a sketch line here. Okay, and so we're going to reflect it across here, and it's going to be so many units away, so it's going to look something like this as it's reflected across here. And then we're going to take and draw another line, reflect it across this line, perpendicular. Okay, as reflect across this line, it's going to be the J, and this is kind of hard to draw. The J will be something like this. Now, of course, it's not, but it should be the same size all the way through. So, as we look to see what is our points across here, well, if we drew a line from here to our intersection point, this angle should be to right here. So, and then we'll do another one from here to here. So, center point of this one's going to be C. Okay. And so what we have is we have our first angle here. We have angle 1. That's our first angle. Okay, we have angle 2. This one. We have angle 3, and we'll call this angle 4. So how many degrees do we move? Well, this whole thing is 70. So we know that angle 2 plus angle 3 equals 70. So angle 2 plus angle 3 is equal to 70 degrees. Okay? And we know that angle 2 and angle 1 should be the same. Okay, so we know angle 1 should equal angle 2. And we know that angle 3 should equal angle 4. So that means that if these two are going to equal 70, then angle 1 plus angle 4 should also equal 70. So if we add up all of our angles, so that means that angle 1 plus angle 2 plus angle 3 plus angle 4 should equal 70 times 2, which is going to be 140 degrees. So that is how many degrees we've rotated all the way through. So to kind of help you see, it's a rotation. If we go start here, now this is probably not going to be exact because the way I drew it, but it's going to be a rotation as it goes through all the way to this point over here. It's been rotated, and it's going to be 140 degrees, and it's going to be 140 degrees clockwise rotation. All right, so I want you to do part B. Pause the video. In fact, this will be the end of part 1. When you come back to part 2 of lesson 9.4, you will get the result of this and the last few examples.